This video is for Senior Design 2, ECE 4960, Spring 2018 semester. This is for Team BR5. The team of BR5 consists of Hunter Booth, Corey Rondeau, Chandler Schramm, Avery Wood, and Zack Woods, and our project was the balancing robot. In this video, we will go over the problem statement, the physical system, the electrical system, the software system, and the final design and a demonstration video. The problem statement is the goal of this project is to develop a two-wheel balancing robot inspired by the Segway. The robot should be between 14 and 30 inches tall. The center of gravity should be at least 4 inches above the axle, and the robot should be able to balance and be able to receive pushes and regain balance. Able to be controlled using Bluetooth. The Bluetooth commands will allow the user to drive the robot. The robot should be able to go up and down ramps as well as go over or around obstacles while under control of the user. The physical system was designed to be used as a robust frame that will allow easy access and a protective housing for electrical components. We began using an aluminum C-channel design. We also added Lexan on the frame to add to the robustness of the system as well as give a place to mount electrical components. We added motors and wheels to the frame. Driver was added. This allowed the robot to move. The goal of the electrical system was to distribute power and signals through the system. The power and signal distribution would control the robot from the software. Some mechanical protection was necessary for electrical components to not be damaged in the event of the fall. The two mechanical protection components were the Tiva bracket and the battery holder. The Tiva bracket, which can be seen on the left side of the screen, allowed the Tiva to have a good mounting position since no mounting holes are provided on the Tiva. The battery box on the right hand side allowed the battery to have a good place to be mounted since it is the heaviest of our components. The battery box is self-centering in the C channel so that it does not bias the robot in any direction. Next, we wired the robot. In the middle picture on the top, you can see the Tiva. In the middle of the robot, you'll see the motor driver, and then about 3/4 of the way down the robot, you can see the power distribution from 12 to 5 volts to run our logic. The batteries in the bottom as well as the motors. The IMU is approximately at the center of gravity 4 inches above the axle, and our Bluetooth module is in the top left. Both the IMU and the Bluetooth are covered up by the C channel. Two important characteristics of our robot was a safety cutoff switch. This allowed the user to cut the robot off completely in the event of a crash or other problem. We also had a safety fuse. This safety fuse protected all of our components from wire shorts. All wires were heat shrink, but in the event of a short, the fuse protected that. Also, if the motors were getting too hot or stalled, this fuse would pop instead of burning up the motors. The software system had two parts, balancing and driving. Balancing was the most important process. Driving came from user inputs through Bluetooth. This model is both the balancing and the velocity model, which allowed driving. It receives inputs from the IMU as feedback of body angle and converts that body angle into a torque, which is half of the torque is applied to one motor, half the torque is applied to the other, so that the robot does not receive too much. This model is unpacking Bluetooth commands. This allowed us to go forward and backwards. We could have gone left and right, but did not have that code implemented. In the final design, the robot balanced and was able to be driven forward and backward from Bluetooth. Now we will show a video of our robot actually working. Our robot had some status lights. It had green for backwards, blue for balance, and then white for forward. We're going to put it in the balance mode here, as you can see by the blue status light. We're going to show that it balances. going to show it going up some ramps here. We have added the leash because the end pieces of the ramps are not very long, so that the robot does not fly off the end. Here we set it in the white position, which is the forward. It goes up this short ramp, or the shortest ramp, goes up a little taller ramp, and balances very well at the end of that ramp. We attempt to go down the ramp. It does not do as well, but it does go down the ramp. And then we go up the tallest ramp. Here it's built up so much speed at the end, it's hard to get it to stop at the end of the ramp. Thank you for watching our video, and have a great day.